pull a box at an angle, or if we push a box at an angle. That's what we did yesterday. My thing now is, what if the box is sitting on something that's at an angle? So let's just do it, okay? I got a box here, and it is sitting on something at an angle. We'll just call that angle theta, all right? There's nothing else interacting with this box, but let's say the box is at rest. If we say a box is at rest, we can also say what? All the forces are balanced, right? Cancel each other out. My question is, what do those forces look like? Okay. Malachi can have his redemption shot. Malachi, what is that downward force affected from gravity called?
Weight.
Weight. There we go. All right. Weight. Weight is still downwards. Gravity is still downwards. All right. What really gets changed is the direction of force normal. So normal is a math word, a mathy term for the same thing as saying perpendicular to. So what is a direction that's perpendicular to the surface it's on? That's going to be going this direction. Force normal is that way. This box wants to slide down, right? It wants to slide down the ramp. What's that force that prevents motion? Friction. Friction opposes motion, so friction is going to be going up the ramp. Cool. Now, I've seen a couple of different methods on how to approach this problem. This is the method I use. I do not have time in class to go through all 3 different methods of doing it. If you want to watch Khan Academy videos and do it that way, you're welcome to. These notes I have here are using another method that I don't typically tend to use, and even more specifically, how it's mentioned in the notes right here. Nope, wrong slide. Right here. I don't do this thing. You can have this method where you like literally tilt your head and change your frame of reference and draw your free body diagram. I don't like that. That makes me uncomfortable. Instead, I just like to do it this way. What I'm going to do is we've got our free body diagram drawn. I'm actually going to redraw it. And you guys should always be in the habit of redrawing your free body diagrams. So I'm going to take my box, which is at an angle. I'm going to redraw it. So we got weight downwards, force normal, and then we got friction going up. Now I'm ready to break things into my components. The thing we're going to break into its components is actually going to be weight. If we look at weight and break it into its components, instead of calling it x and y, right? Because that's what we'd have to do. If we tilt our head, we can call it x and y at that point. I like to call it weight perpendicular, or the weight that's pushing into the ramp, and weight parallel, weight that's going parallel to the ramp. Looking at that free body diagram now, can you see what forces are counteracting each other? Weight perpendicular and force normal. Let's do a little highlighter action. Force normal and weight perpendicular. Hey, look at that. Those are going opposite directions, right? Those are in balance with each other. What's the other one that's going to be in balance with each other? Weight parallel with friction. Okay. Because those are going opposite directions. The only thing is, and I just want you to like swallow this pill and just take it as truth. You're welcome to go to Mr. Weimer's room and go down this geometry rabbit hole, or you can just accept it as truth. Whatever angle your ramp is, whatever angle this is, that angle is the same thing. Okay? We could do like a whole geometry proof on it, do a whole list of things, just don't worry about it. Just take it as truth. So since the object's at rest, what I could say is, well, the summation of my forces equals 0 for all directions. And from there we can say weight perpendicular equals force normal. And we can say weight parallel equals force due to friction. Not too crazy, right? I mean, it's just there. I mean, it's one of those things you look at the first time and you're going, holy cow, right? Especially if I just showed you that picture first and you're like, what in the heck's going on? Your eye doesn't even know where to process first. But this, I think, is a much easier approach. Could we go down the rabbit hole and expand these even further? Well, sure. Do I have a formula for frictional force? Well, yeah. So this could be like mu sub s force normal equals weight perpendicular. You could do that. Could we expand it just a tad bit more? And this is probably the one step that most students are like, oh, ramp problems. I got an angle here, right? I got a triangle. Weight perpendicular, weight parallel, we got an angle. Anytime you see an angle, we do what, Reese? Trig. That's probably going to be your go-to answer, all right, for almost everything this year. Anytime you see an angle, trig, all right? Until we hit second semester, and then that's not going to be the answer anymore. So, we could expand these just a tad bit more. I don't want to go down that rabbit hole too much. We could expand those a little bit more into their trig functions, because we have weight, and if we're looking for parallel, that would be sine, right? So we could expand this as weight sine theta equals mu s force normal. The other one would be cosine. So this could be weight cosine theta equals force normal. We could expand those if we need them, right? Sometimes you don't. So sometimes you don't have to go that far down the rabbit hole. Usually you have to under one situation, and that is if you're trying to find coefficient of friction. Can I show you just a tad bit more magic? I'm going to do some math magic, and you're going to have a shortcut. And if you remember the shortcut, you can use it for the rest of forever. Anytime you're trying to find coefficient of friction of an object sliding down a ramp. I just love this because it's like math magic. And like, it simplifies out that much? It sure does. Do we see how I have force normal? Right? Could I plug that in over here? I sure could. Let me do that. Trooper, don't get ahead of me and ruin my surprise, okay? W sine theta equals mu s force normal is the same thing as W cosine theta. Hey, does something cancel out on both sides?
Sine W.
Just W, right? Weight cancels. So then I get sine theta equals mu s cosine theta. Can I get coefficient of static friction by itself? Sure. We divide both sides by cosine. So I get mu s equals sine theta over cosine theta. Which is what, Troop? Sine over cosine? Tangent. So, now you got a little hidden gem in your back pocket. If you're looking for coefficient of friction, either static or kinetic, you just know it's tangent theta. Cool. What time we get out here? I don't think it's the same time, is it? It's 12.
50. We get out of lunch at 20.
Yeah, it's 50.
It's 50?
Wait.
Mine says 12 o'clock here.
So it'll be 12.
B lunch ends at 12.
I'm all over the place.
What time is it?
It's because we got here at 11.
Alright.
About, okay.
Alright, here's what we'll say. I'm going to leave it at that. I'm going to leave example 4 for tomorrow, actually, because it's expanded on a little bit more. Because we have an object with some tension as well. We'll save that for tomorrow.
So is there no force applied